So that was ways to sample from a given 1D distribution. It was very easy. In the case that it was discrete 1D distribution, a little bit trickier, involved some derivation, but we can do it pretty easily for continuous 1D distributions as well. What about in a multivariate setting? That is, we have, for example, a Bayesian network indicating a probability distribution over a whole set of variables, and we want samples from those variables. So option number one, let's say we just want samples from one of our variables, but in the context of all those other variables. So we want to marginalize away the other variables, we get just the distribution for the variable we care about, and we want the samples from that variable. So option one would be to do probabilistic inference according to the methods that we saw last week. That would give us our 1D distribution, and then we could sample from that 1D distribution. Now that wouldn't give us joint samples, that is, it wouldn't give us samples from many of the variables, and it also wouldn't work if we couldn't do sampling, or if we couldn't do inference efficiently. For example, if our Bayesian network is a non-tree Bayesian network, or more generally, one that has a high tree width. Option number two, so let's say we're not going to do inference. Option number two, let's say we just want to sample from a Bayesian network with no evidence. That is, we haven't observed any of our variables. Turns out that's very easy. The way I do that is recall that in a Bayesian network, I have a probability distribution for each variable given its parents in the distribution. So the way I can sample from a Bayesian network is I just go in topological order of my variables such that I always sample parents for children. I sample A according to the probability of A given by the Bayesian network. Then I sample B according to the distribution probability of B given A. So these are all going to be 1D samples, so we use the methods from the last section. That's going to give us samples which come directly from our Bayesian network. So that's really easy, no problem, even for a high tree width Bayesian network. That method I just told you, that's called forward sampling. Okay, but what if I have some observed values? That is, let's say I've observed D and E, and instead of producing values from probability of A, B, C, D, E, that's the distribution that forward sampling would give me. Let's say instead I want the probability distribution for A, B, C given D and E. By the way, now even the inference method is going to be tricky, right? Because recall that when I have evidence, that makes my inference hard, generally. Okay, so here's the distribution I want. I can use the following method. I just run forward sampling in exactly the method I just said. Generate A, then C of A, then E given C. So I have values for all of my variables. And then I ask, did the values I happen to generate equal those that are in my evidence? If they do, then great, I accept this, and that's my sample. Otherwise, I reject it, throw it away, and start again. Now, it's pretty easy to show using exactly kind of the reasoning we did for the 1D rejection sampling, that rejection method, which is called, by the way, logic sampling, logic sampling will give you samples exactly from probability of A, B, C given DE, which is exactly what we want. The only problem is that its running time, as usual, is proportional to 1 over our accept chance. So if we have a very small amount of evidence, then that's no big deal. We just have to run forward sampling a couple times until we find a sample that happens to match our observed values, and then we're good. We have our samples, or the sample we want. But if we have a large amount of evidence, which is very standard for big Bayesian networks, for example, in the case of a medical Bayesian network, we might have run 100 tests on a given patient, and maybe only a couple tests, but maybe we had the patient fill out a questionnaire that had 100 questions on it. Each of those questions is going to manifest itself as an observed value in our Bayesian network, and we have to run forward sampling until we get exactly all of those values right. And if we don't do that, then we have to start over from scratch. And that's almost never going to happen. We'll have to run it, millions of times before we'll get a good sample. So in networks with lots of evidence, logic sampling is going to run extremely slowly, kind of unusably slowly. So we're going to talk now about some methods for sampling from Bayesian networks efficiently.